Hey physics. So last time we talked, we were looking at Rutherford's experiment, which showed us which took us from the plum pudding model to the nuclear model. The nuclear model says that at the center of an atom is a nucleus, which is small, like tiny in fact, and dense and positively charged. So some things that we know based on that are that all the positive charge in an atom is contained in the tiny, dense nucleus at the center of that atom. You can kind of think of the nucleus like the house where all the positive stuff in the atom lives. The nuclear family lives together in the same house. So what we know is that the positively charged particles in the nucleus are called protons. And here is my artistic rendition of a proton. Each proton has a charge of +1. So you can think about, it's super simple. These are like the smallest units we can hardly work with. So proton equals +1. Has a positively charged electric field that looks like that. Electrons, on the other hand, have a charge of -1. So they balance each other out. One proton for one electron. If there's one of each, then they're neutral. The atom is neutral. So even though they're small, electrons have the same amount of charge as a proton. However, the electron's charge is negative, so balanced but opposite. This is a negatively charged electric field pointing inwards. So now that you've got that, let's do some math about it. So this hydrogen atom has one electron and one proton. So that's going to balance each other out. They are going to be neutral. This alpha particle, which is what Rutherford shot through the gold foil in the last experiment, which is also a helium atom with no electrons, has no electrons and 2 protons. So protons are positive, so it's going to have a +2 charge. Okay, so this fluorine atom has 10 electrons and 9 protons. Means there's one more electron than there are protons, so that's going to have a negative charge since electrons are negative. 9 are going to balance each other out, and then there's going to be one -1 hanging on. This gold atom has 79 electrons and 79 protons. You don't have to count them, just take my word for it. So since the electrons and protons balance each other out, it's going to have a neutral charge. So no big deal, right? Now that you've mastered charges, let's get good at calculating atomic mass. So each proton has a mass of 1 atomic mass unit, charge of +1, mass of 1 atomic mass unit. Electrons have a mass of 1/1000th about of an atomic mass unit, which means that you don't have to worry about electrons when you're calculating atomic mass at this level for sure. At some point, with big enough atoms, they're going to add up, but you don't have to worry about the mass of electrons, really. But there is another particle that weighs into an atom, and it lives in the nucleus, and it is called the neutron. And this is my artistic rendition of a neutron, because it is feeling kind of neutral, kind of just not sure, not happy, not sad, just kind of like, I don't know. So each neutron also has a mass of 1. So we have protons with an atomic mass of 1 and neutrons with an atomic mass of 1. And they both live in the nucleus, protons and neutrons, but the neutron's charge is neutral. So to review, the electron, the charge is -1, the mass is tiny, 0.001 atomic mass units. The proton, the charge is +1, and the mass is 1 atomic mass unit. The neutron, the charge is neutral, so you can mark it like a 0 or like a O, and the mass is 1 atomic mass unit. So let's do some atomic mass calculations. So this is a helium atom, not an alpha particle, but a helium atom. It has 2 protons, 2 neutrons, and 2 electrons. So the atomic mass of this atom is going to be 4. 2 protons plus 2 neutrons. The electrons don't count. Okay. So this carbon atom has 6 protons, 6 neutrons, all here in the nucleus, and 6 electrons. So the atomic mass here is going to be 6 plus 6, so 12. This oxygen atom has 8 protons, 8 neutrons, and 8 electrons, because it is balanced, has a balanced charge. 8 protons plus 8 neutrons is going to be 16. But wait, here's a question. With all those protons so close together in the nucleus, why don't they repel each other and fly apart? That's because of the strong nuclear force, okay? So the strong nuclear force works only at super duper small distances, like the distance between, or the size of the nucleus of an atom, like really, really, really small distances. The strong force overcomes the electromagnetic force and prevents the electrical repulsion of protons from blowing the nucleus apart. So something that I think is a fascinating extension of this is that if you think about, it takes an astonishing amount of energy to overcome the strong force. So the nuclei of the atoms inside your body and the atoms inside most things have been the same since the last time they were digested in the sun or in some kind of solar explosion. I mean, the atoms that are inside of our body, the electrons move around, right? Electrons move. We don't keep any electrons. They just are constantly flowing through us. But the protons and the neutrons pretty much stay in that same atom forever unless something really crazy happens. So I just think that's really interesting. So we were talking about the strong nuclear force, and that is one of 4 fundamental forces, one of which is gravity, which you're familiar with. This is Newton with the apple falling on his head. Another one is electromagnetism, which you are also familiar with. That's the forces of attraction and repulsion, and like and unlike charges. We have the weak nuclear force, which is related to radioactivity. It's pretty complicated. We're not going to get into that right now. Just know that it's one of the 4. And then there's the strong nuclear force, which holds together atoms, big and small, keeps all of those protons and neutrons together in the nucleus. Tight, tight, tight. The strong nuclear force holds the nucleus together. Now, there are barriers to the strong nuclear force. When we get really big atoms like this, like uranium-238, this is actually a radioactive atom, and what that means is that it's so big that the strong force is not physically able to hold it all together. So we start getting things like alpha particles coming off of it because it's trying to get to that point where it's stable again, where that strong nuclear force is holding it together. Most of the atoms in the world that we exist in on a regular daily basis are much smaller than this. They're things like carbon, which has an atomic mass of 12. Oxygen, which has an atomic mass of 18. There's a few things that make up most of the substances in the world. Uranium is not one of those things. So these radioactive atoms are pretty rare. So here's a graph of how these different forces work. You don't have to study this super closely. I just want you to kind of have a visual of the difference between these 4 forces here. So to scale here, we have the strong nuclear force, which gets really, really strong the closer that those particles are. This circle here is showing the size of the nucleus of an atom. So that strong nuclear force, that attractive force, gets stronger and stronger the closer they are together. It just holds them tight there. The electromagnetic force is strong all the way, outside of the nucleus. It's big enough to hold all the electrons close because the negative electrons are attracted electromagnetically to the positive nucleus, which is holding the protons and the neutrons. Then not to scale, we have the gravitational force. This is going to be a lot smaller. It's going to work over a much greater distance. And then we have the weak nuclear force, which works within the nucleus, but it's a much smaller force there. So these are not to scale. But I just wanted to show you the strong nuclear force versus the electromagnetic force. Let's do a couple more problems here. So this calcium atom, we're getting a little bigger here. This calcium atom has 20 protons, 20 neutrons, and 18 electrons. So the overall charge is going to be the protons minus the electrons. So it is going to have a positive 2 charge. And the atomic mass is going to be the protons plus the neutrons. So that's going to be 40 atomic mass units. Okay? This gold atom has 79 protons, and as atoms get bigger, they require more neutrons to hold them together. You will notice this in a few different things that I'm showing you here. So this gold atom has 79 protons, 117 neutrons, and 80 electrons. So the overall charge looks like there is going to be a -1 charge. We can see that by going 79 minus 80 equals -1. So that's a -1 charge. So then the atomic mass is going to be the protons plus the neutrons. And I gave you a hint here because this is what gold looks like in the periodic table of the elements. Remember, each one of these atoms has a spot in that periodic table as one of the building blocks that makes up our world. This is the atomic number, and that tells you how many protons are there. This one is the atomic mass number, so 79 protons plus 117 neutrons. Each one of those has 1 atomic mass unit, so adds up to a total of 196 atomic mass units. And then this is probably the electrons, I would guess. So then this platinum atom has 78 protons. This is right next to, see, gold has 79 protons, so its atomic number is 79. Platinum has 78 protons, so its atomic number is 78. Same number of neutrons and 76 electrons. So if we have 78 protons minus 76 electrons, we're going to come up with a positive, like a +2 charge, and an atomic mass, which you can see right here, of 195 atomic mass units. So here's something fun. This is a man-made element called americium, and it was created when scientists were experimenting with the stuff to make, like nuclear science, to make nuclear bombs and things like that. And they were also developing like nuclear power. I mean, just there's so much that goes into nuclear science. So how much atomic mass does an atom of americium, a man-made element, have? So we can find that because I can see here that there are 95 protons in this atom, and there are 148 neutrons. So let me do some math about that real quick. 95 plus 148 equals, so this is going to have an atomic mass of 243. And here is an interesting one. Hold on a second. It's not wanting to go down. Let me make it. Oops. I'm trying to get to my very last slide here. There we go. Okay. So this is an example of a real-life molecule. This is a polypropylene molecule, which is plastic. And we know from our experiments earlier that polypropylene, or plastic, likes to give up electrons and gain a negative charge. It likes to gain electrons and gain a negative charge. So what would we need to know to calculate the charge on this polypropylene molecule? So there's a few things here. You need to know what each one of these atoms are, because each one of these balls represents an atom. So when we're looking at ball and stick models like this, the black atoms represent carbon. The white atoms here represent hydrogen. Red is oxygen. Blue is nitrogen. And these green over here are fluorine, sorry. So you would need to know a lot of things to find out the charge on this polypropylene molecule. You want to know how these atoms are sharing their electrons, what they're going to give up easily, what they're not going to give up very easily. There's a lot that goes into that, and that ends up being what you learn in chemistry. So we'll leave it at that for right now.